In this chapter, we will talk about the definition and formula for translational kinetic energy, and then the definition and formula for rotational kinetic energy, and then the derivation of the total kinetic energy formula for a bicycle, and the effect of rim diameter. And it won't surprise you that there's lots of math in this chapter also. From eloquent theories sublime, famous names echo through time. Joule, Newton, and Watt, good poem names I've got. With Pascal, nothing will rhyme. When a bicycle is moving, we have two types of energy. We have translational kinetic energy and we have rotational kinetic energy. This chapter goes into the formulas for each of those and then shows how we can combine them into a single equation for a moving bicycle. The total kinetic energy is going to be the sum of the translational kinetic energy of the rider and bicycle plus the rotational kinetic energy in the wheels. This lengthy expression can be abbreviated like this, and then further by this. We will first figure out the translational kinetic energy, and then the rotational, and then combine them into an expression for the total. In looking at this figure here, the translational kinetic energy is given by this expression, 1/2 mv squared, and in the SI system, mass is in kilograms, velocity is measured in meters per second, kinetic energy is in kilogram meter squared per second squared, and 1 kilogram meter squared per second squared is 1 joule. So our term on the left becomes this, where B stands for bicycle and C for cyclist. The rotational energy is on the right, 1/2 I omega squared, which is kinetic energy of rotation is 1/2 the moment of inertia times the rotational velocity squared, and these are the units. Moment of inertia is kilogram meter squared, and rotational velocity is in radians per second. As a reminder, radian is a dimensionless number. If I want to, I can express my unit for omega rotational velocity. I just slash with a second symbol in the denominator and nothing in the numerator. Since in my calculation I'm going to be squaring the rotational velocity, I have to square the unit as well. When I combine these two terms, I get kilogram meter squared per second squared, and that is the unit of a joule. When I combine the translational and rotational components, I get that expression in the middle, but there's got to be some way I can combine those terms and simplify that a little bit. And the question is, how do I do that? Let's work through a hypothetical, which is that Sam is pedaling his bicycle at 20 miles per hour. What is the total kinetic energy of Sam and the bicycle? With respect to translational kinetic energy, this is what I know or can easily determine. One is Sam's mass in kilograms. I have a conversion factor. 1 pound equals 0.450 kilograms. Likewise, I can determine the bike's mass in kilograms. I can determine the velocity in meters per second because I know that 1 mile per hour equals 0.447 meters per second. So that allows me to compute the translational kinetic energy of 1/2 mv squared. With respect to rotational energy, this is what I know or can easily determine. The mass of the rims and tires in kilograms, and I know that the mass of the rims and the tires is overwhelmingly responsible for the moment of inertia of the wheel. I can also easily determine the radius of the wheels in meters, and that will allow me to compute the moment of inertia. Here's the expression for the rotational kinetic energy. We know how to compute the moment of inertia, but what about the rotational velocity? So let's look at this further, because I know that somehow the velocity of the bike has to be related to the rotational velocity of the wheels, but what is that relationship?
Let's look again at this graphic you've seen before and see what happens to the wheel as the red dot on the front wheel rolls out one complete revolution.
So this is our rollout distance for one revolution of the wheels, and that is, let's say, 2.12 meters. That would be a typical rollout distance for one revolution of a road bike wheel, and it's 2120 millimeters, and that is what I would program into my bicycle computer. Now the distance that red dot travels is clearly 2.12 meters. The distance here that the red dot travels has to be the same as the distance that the bike travels. The circumference of my wheel is 2 pi times the radius, which is 2 pi times 0.338 meters, which is the radius of the wheel, and that has to be equal to 2.12 meters. Here is the wheel at the start. We're going to let the wheel roll out one complete circumference. The wheel has had 2 pi radians of rotation. Let's do the same thing with the bike. As the wheels of the bike rotated 2 pi radians, the bike itself moved 2.12 meters. If it takes 1 second for the bike to travel those 2.12 meters, then the velocity of the bike is 2.12 meters per second, which works out to 4.75 miles per hour. As the wheel rolls one revolution, the velocity of the red dot is 2.12 meters per second. Hopefully, after all this, we can see these relationships that 2.12 meters is radius times 2 pi, and that's the circumference. So the velocity of the red dot is the radius times 2 pi radians per second, and that's the radius times the angular velocity of the wheel, and that is also equal to the velocity of the bike. So the velocity of the bike in meters per second is equal to the radius of the wheel in meters times the angular velocity of the wheel in radians per second. We're now in the position where we can simplify this expression for the total kinetic energy. Let's go through this calculation slowly. I'm going to use as I, for the moment of inertia, the mass of the rim, tire, and tube, because you recall that accounts for over 90% of the total. That in turn is multiplied by r squared. So I get this expression: the kinetic energy of rotation is 1/2 the mass of the rim, tire, and tube combined, multiplied by the radius squared times omega squared. But I know that velocity is also equal to the radius times omega, and I can rearrange that to get omega equals velocity divided by radius. So into this expression that I had 3 lines above, for omega I can substitute velocity divided by radius, which gives me this. I can cancel out r squared. The rotational energy just becomes 1/2 the mass of the combination of the rim, tire, and tube times the velocity squared. That is going to be per wheel, so I just multiply that by 2, which removes my 1/2, and that gives me the rotational component for both wheels at the same time. So let's again fill in this box and see if we can come up with something simpler than what we had above. We add together the translational component,
and the rotational component. Notice that there's no 1/2 in front of the mass of the rotational component because that represents both wheels. Here I just factor out velocity squared, and I get 1/2 the mass of the bike and cyclist plus the mass of the rim, tire, and tube, all multiplied by velocity squared. Note this, the wheel size, that is the diameter, is not a term in the calculation of total energy, and because it's not intuitively obvious that that may be the case, I'm going to prove it to you with a few graphics. Here's a circle, we'll call that radius 1. There's another length of radius 1. The distance from there to there we know is 1 radian. Here is the center of a wheel. There's the rim. Pi measurements. It's a 650B wheel with a bead seat diameter of 584 millimeters, which gives us a radius of 292 millimeters. That distance there is 1 radian. We'll call that D1. Here's a larger rim. That's going to be a 700C or a 29er. Bead seat diameter of 622 millimeters. Radius, we'll call that R2, of 311 millimeters. And that distance there is D2. And clearly the length of D2 is greater than the length of D1. If each of these wheels turns through an angle of exactly 1 radian, the D2 wheel with a longer arc will travel a greater distance simply because the length of the arc is greater, corresponding to 1 radian, than is the case with D1. Wheel 1, with a radius of 0.292 meters, has a circumference of 1.83 meters. Wheel 2, with a radius of 0.311 meters, has a circumference of 1.95 meters. So if the velocity of bike 1 equals the velocity of bike 2, let's say they are going at 20 miles an hour, which is about 9 meters per second. If velocity equals radius times omega, then omega equals velocity divided by radius. The rotational velocity of the wheels on bike 1 is equal to 9.0 meters per second divided by 0.292 meters. That's 31 radians per second, which is 4.9 revolutions per second. With bike 2, we divide 9 meters per second by 0.311 meters, and that is 29 radians per second, and that works out to 4.6 revolutions per second. The obvious point here is that the green wheel rotates the fastest, but covers less distance per revolution, and the blue wheel rotates more slowly, but covers more distance per revolution. Which has illustrated what we said earlier, that in the total energy computation, the wheel size is irrelevant.